Hi everyone. Today we're going to be looking at our notes for 9.1 vectors in two dimensions. I want to start just by defining what is a vector. A vector is a line segment with an assigned direction. Okay? A vector is a line segment with an assigned direction. So everything we know about line segments, they have a finite length, they have two endpoints, but now it has an assigned direction. So as we move across the line segment, we move across in one direction, whereas line segments, just as they don't have a direction. It's just the segment. Okay. Some properties of vectors. Vectors have magnitude and direction. Okay. Vectors have magnitude and direction. So when we think of magnitude, you can think of that as like the length or the size of the vector. So just like a line segment has a length, it's got a defined length, the vector has a defined magnitude, the size of the vector. It's also got a direction, right? That's the assigned direction piece. So on the xy plane, vectors have component form. V equals, so we're calling this vector V, is equal to, we've got these angular brackets, delta x, delta y. Okay, so this vector is defined as this bold letter V. So instead of saying a variable V, we denote vectors by using bold lettering. So if you're writing this in on paper, you can just be sure that that V is bolded to denote a vector. And then we've got these angular brackets. So not to be confused with like an ordered pair or anything like that. We use these angular brackets to denote the component form of a vector. So this would say vector V is delta x, delta y. Okay? So this is the component form, and the magnitude of this vector is denoted as such. It looks like the absolute value of v, but because we're talking about vector v, this means the magnitude of vector v. And this is given by the expression the square root of delta x squared plus delta y squared. And you might recognize this as the distance formula. In fact, we can think of a vector. If I were to draw this on the xy plane, if I were to say that this is vector v, the length here is our magnitude, and then the direction here, we're pointing in up and to the right. So this would be the assigned direction for this vector v. Now you might notice, I'm going to use a different color here. If I were to break this down into its horizontal and vertical components, delta x and delta y, you might notice that we can draw this as a right triangle. Therefore, the vector, the magnitude for the vector, is given as the hypotenuse of this right triangle, which makes sense if we're denoting the magnitude of the vector using the distance formula. It's the distance delta x and the distance delta y. We can use Pythagorean theorem to solve for the hypotenuse. And then if we take the square root of the hypotenuse squared, then we're given just the length of the hypotenuse, or just the magnitude of this vector. Okay? Now let's see a few examples. So example 1, given vector u and vector v, draw the given resultant vectors. So now we're going to do operations on vectors. And in fact, operations on vectors is very similar to what you might be thinking. So if we have vector u plus vector v, we simply add these vectors together. Now we do so in a special way. We have to add them tip to tail. Okay, when we add and subtract vectors, we have to do tip to tail. So what I mean by that is if I'm drawing vector u, and then I want to add vector v, well, let's start by drawing vector u. So vector u is about this length here, and it's in this direction. If you have a ruler, that's even better. You can measure it draw a straight line and draw that arrowhead. Vector v is going down and to the right, and it's got a shorter magnitude, a smaller magnitude. Tip to tail, I'm going to take the tip of u and attach it to the tail of v. Therefore, the resultant vector, if I start from the tail of u and go to the tip of v, I would have this resultant vector here. So I'm going to go ahead and label these vectors. We have vector u, vector v, and then this resultant vector is u plus v. And again, always remember to bold those vectors. We want to denote vectors, not variables. Now, u minus v, you might know as this would be similar to writing u plus negative v. Okay? So what putting a negative in front of a vector does is it reverses the direction. So what we can do is we can just add these two vectors, but now we're going to reverse the direction for v. So we'll start with u. And now, so this would be u. And now for v, instead of going down and to the right, the negative v is going to be up and to the left. So this is going to be negative v. So then the resultant vector is going to be more up and to the left than the u plus v. So the resultant vector is vector u minus vector v. Okay? Now this last one here is saying 2v. We're taking v and we're multiplying it by 2. This 2 out in front is what we would call a scalar. Scalars only have magnitude, okay? They do not have direction. So if I were to just say the number 2, 2 is simply a scalar. So scalars just have magnitude. And just to be clear, I'm just talking about 2 right now. So any scalar is just a quantity, right? It's just telling me the size of the vector. It's not saying anything about direction. So 2, 10, -5, 1 million, right? Even irrational numbers like the square root of 2 or pi, things like that. Any just plain old number is considered a scalar, whereas once you assign that direction, now we're talking about a vector. So if I wanted to draw 2v, we would start with v, right? Here's 1v, and 2v is going to be double that in the same direction, okay? So this resultant vector is going to be 2v, all right? All right, let's go ahead and try example 2. Given an initial point, 2, 1, and a terminal point, 8, 5, draw the vector, write the vector in component form, vector v, and find the magnitude of vector v. All right, so we'll start with the initial point, 2, 1. We'll go ahead and plot that point. The terminal point is that ending point. That's going to help us determine the direction. We have 8, 5. So we'll go ahead and plot that point as well. Vector is going to go from the initial point to the terminal point. So we're going to extend that line and then draw that arrowhead. Remember, this is a vector, so we do need to denote that direction. To find the component form, what we can do is find delta x and delta y. So vector v is equal to delta x, comma, delta y. And to find delta x, we have our change in x values. So we have 8 minus 2, and our change in y values, 5 minus 1. So then our delta x, our x component, is going to be 6, and our y component is going to be 4. So we could also write vector v as 6, 4 with those angular brackets. To find the magnitude, we can simply take the square root of the sum of the squares of the change in x and change in y, right? So we have the magnitude is the square root of delta x, the quantity squared, plus the quantity delta y squared. This is equal to, we have the square root of 6 squared plus 4 squared, which is equal to the square root of 36 plus 16, or the square root of 52. Now this can be simplified. I know that 52 has a perfect square factor of 4, so this can be simplified into 2 to the square root of 13. And yes, I do want you to simplify those roots whenever possible. Okay, so this means that the length of vector v is 2 times the square root of 13 units. All right, go ahead and flip the page. Example 3. Now I've given you the vector in component form and the terminal point. Now I want to know, where does this start? Okay, so a couple ways we can do this. I know that we can find the vector in component form if I take the difference of the terminal point and the initial point, okay? So what I can do is set up and I can set up an equation. I can say that my vector, my resultant vector, 2, 7, angular brackets, is equal to delta x. So if the terminal point is -2, we would subtract the initial point, okay? Um, oops, I want an angular bracket there. And then our change in y is going to be our terminal minus the initial. Oops, no, also not right. So let's do y, there we go. Terminal minus initial, angular brackets. And then we can solve for x and y. So -2 minus a number gives us 2. So I can go ahead and set up two equations. -2 minus x equals 2. And we have 4 minus y is equal to 7. Solving for x over here, we add 2 to both sides. And we get -x is equal to 4. So therefore, x is equal to 4. Okay? I'm sorry, -4. X is equal to -4. Solving for y, we subtract 4 from both sides. We get -y is equal to 3, so therefore y is equal to -3. So my xy ordered pair is -4, -3. All right. Example 4, given vector u and vector v below, find the indicated vector. So we'll start with the first part, part A, where we have 2u. Okay, so I know that u is defined as, well, it starts at the origin and it ends at -2, 3. So therefore, u can be defined as the vector -2, 3. Now, if I wanted to multiply this by the scalar 2, I can just simply put the 2 out in front and distribute it into each of the components, x and y. So if I distribute that 2, we have the resultant vector -4, 6. Okay. This should say part B. So for part B, -v, well, we can write v as, let's see, we have 3, 4. So that -v, we distribute that negative, we simply get -3, -4. Okay. And finally, for part C, we have 3u minus 2v. We're going to start by writing out 3 times u. So remember, vector u was -2, 3. And then minus 2 times vector v, which we know was 3, 4. So distributing the 3, we get -6. And then we get 3 times 3 is 9. So this is 3u. And then distributing the -2, we get -6 and -8. Okay. At this point, we're just adding these vectors. So what we can do is we can add the components. So add the x components together, add the y components together. So the x components, -6 plus -6 is -12. The y components, 9 plus -8 is +1. So the resultant vector, -3 minus 2v, 3u minus 2v is -12, 1. Okay, now let's talk about the unit vector. Similar to the unit circle, the circle centered at the origin with radius 1, that's that unit piece. The unit vector is simply a vector with magnitude 1. So let's go ahead and write that out. Unit vectors are vectors with a magnitude of 1. All right. The most common unit vectors, are the unit vectors I. So remember, that's a bold I. This is a vector, which has component form 1, 0. And j, which you guessed it, has component form 0, 1. And again, that j is bold. This is a unit vector. Okay. So remember, unit vectors have magnitude 1. Example 5, I want to know, is vector w a unit vector. So here I have the component form 12/13 and -5/13. And I want to know, is this a unit vector? Well, we know unit vectors have magnitude 1, so let's find the magnitude of W and see if it's equal to 1. If it is, then this is a unit vector. So we use our magnitude formula. We have the quantity 12/13 squared plus the quantity -5/13 squared. And so we get 12/13 is 144 over 169. And then plus the -5/13 squared is equal to positive 25 169ths. We have the same denominator, so we can just add the numerators. 144 plus 125 is 169 over 169, which reduces to 1, and we know the square root of 1 is 1. So yes, W is a unit vector. Okay. All right, example 6, how can we write vector u in terms of I and j? Well, I can write this. I know that the horizontal component is 5 and the vertical component is -8. In fact, we can write this vector as 5i minus 8j. Now, why can we do this? The reason why is if we were to expand this out, 5 times the unit vector I, 1, 0, minus 8 times the unit vector j, 0, 1, then we would end up with vector u. So we would get 5 times 1 is 5, and then 5 times 0 is 0. -8 times 0 is 0, and then -8 times 1 is -8. And then if we were to add these together, remember that adding the components together, we get 5, -8. And so we get the same thing. All right. All right, go ahead and flip the page. Example 7. A vector has length 8 and direction pi thirds. Find the horizontal and vertical components and then write the vector v in terms of I and j. Okay? So if I were to draw this vector, I know that it has length 8 and direction pi thirds. So if I were to draw this, the length would be 8 and that angle is pi thirds. Okay. If I were to draw this triangle, expand it out, this is a right triangle, we'd have our delta x and our delta y. So then my x component, I know that I can set up some right triangle trig. I know that the cosine of pi thirds is equal to delta x over 8, adjacent over hypotenuse, SOHCAHTOA. Then I know that delta x is equal to 8 cosine of pi thirds. Well, I know what the cosine of pi thirds is. That's simply equal to 1/2. So we have 8 times a half, or 4. For the delta y, we can set up a sine equation. So sine of pi thirds is equal to delta y over 8, opposite over hypotenuse. Therefore, delta y is equal to 8 sine of pi thirds. And we know what sine of pi thirds is. That's √3 over 2. And so we have 4 √3 as delta y. Okay? So vector v in terms of I and j is equal to 4 times I plus 4 √3 times j. And as always, please bold those vectors. In component form, this is 4 √3. All right? All right. Example 8, given the vector u, find the magnitude and direction. Okay? So let's go ahead and draw this. It's given to us in terms of I and j. I'm going to go ahead and draw the coordinate plane here. We have a negative I, or x component, you can think, and then our y component is just simply 1. So this tells us we're in quadrant 2. Here's our vector here, where the horizontal component is -√3 and the vertical component is +1. Okay? I need to know my angle theta. So let's start with magnitude. So magnitude. We have the magnitude of vector u is equal to the square root of the change in x, so negative square root 3 squared plus 1 squared. So this is equal to the square root of 3 plus 1, square root of 4, or 2. So the magnitude is equal to 2. Now the direction, this is a vector, so we need both magnitude and direction. So the direction is going to simply be, well, if I wanted to find this angle right here on the inside of the triangle, I could set up a tangent equation. So tangent is equal to opposite over adjacent, SOHCAHTOA. Well, I know that this is equal to, if I were to rationalize this, negative root 3 over 3. Now I'll save you the work. We know how to do this. I know that this is my reference angle of pi 6 in quadrant 2 is going to tell us that theta is equal to 5 pi 6. Okay? So then the magnitude of vector u is 2 and the direction is 5 pi 6. All right? Example 9. Given the vector v, find the direction. So here we have it in component form. So we have a negative x and a negative y. So we have negative 6, negative 4. Oh, I'm going to go ahead and draw that arrowhead. This is a vector. So we have negative 6, negative 4. To find the direction, we have theta is equal to the inverse tangent of opposite over adjacent, negative 4 over negative 6. Okay. Here you're going to have to plug this into your calculator. So we get theta is equal to, in radians, this would be about 0.59 radians. And we know that we're in quadrant 3. That theta that we just got is right here. Well, I know that the negative x-axis is pi radians. So again, quadrant 3 tells us that we're going to take pi radians and we're going to add our 0.59 radians. And that's going to give us our answer, our full angle, all the way around, of 3.73 radians. Okay? All right, last problem, example 10. Given vector u and vector v, find the following. So we'll start with the magnitude of vector u. This is equal to the square root of, we have 3 squared plus 2 squared. And that's equal to the square root of 9 plus 4, or the square root of 13. Now we have the magnitude of 2v. So first things first, I'm going to just find 2v. So 2 times vector v is equal to 2 times negative 1, positive 6. Okay? Which is equal to negative 2, 12. All right. Now let's find the magnitude of 2v. That's equal to the square root of negative 2 squared plus 12 squared, which is equal to the square root of 4 plus 144, which is equal to the square root of 148. I know that 148 is divisible by 4, so this is equal to 4 is a perfect square factor. So therefore, this is equal to 2 root 37. And 37 cannot be reduced, so this is our answer, the magnitude of 2v. Now we have the magnitude of u minus the magnitude of v. Actually, before we continue, one thing I want to point out is that note that magnitude of a vector is a scalar, right? So I should expect my answer to be a single numerical value, not a vector. There's not going to be any direction. Our answer is a single numerical value. Okay, so let's go ahead and do this one. I already know what the magnitude of u is. It's equal to the square root of 13. Now, I also know what the magnitude of 2v is, and that's 2 square root of 37. Therefore, the magnitude of v is half of that, right? So just the square root of 37. Now, these two radicals cannot be combined because the radicands cannot be simplified, and they are not the same. So therefore, this is our answer here. Okay. All right, last one, we have the magnitude of u minus v. So this, if I were to just do u minus v, this would be equal to the component forms. We have, let's write this in terms of I and j. So let's do 3 minus -1 times the unit vector I, and then plus the y component, so 2 minus 6 times the unit vector j. This is equal to 4i, and then plus -4j, or just minus 4j. Okay? If I wanted to find the magnitude of u minus v, then this is equal to, we have the square root of 4 squared plus -4 squared, which is equal to square root of 16 plus 16, or the square root of 32. I know that this is has a perfect square factor of 16, so this is equal to 4 square root of 2. And that's our final answer. So notice that the magnitudes, the difference of the magnitudes is different than the magnitude of the difference. Okay, these two quantities are not equal. All right. So this has been our notes on vectors. We talked about component form. We talked about unit vector form. We talked about direction, magnitude. We also talked about scalars. We're going to get a lot of practice on this, so we'll see you tomorrow. Have a great day, everybody. Goodbye.